Hello, everyone. Today I'm gonna take one step back in the quantum series, coffee shop. So this time I'm gonna talk a little bit about the classical information, and then we move on to advanced topic in quantum informations. So in classical computer, we are dealing with bits, which means that information that we have is just a series of ones and zeros. So we have, for example, 0, 1, 1, 1, 0, 0. And how do we create this zero and ones? By transistors. So transistor basically is a switch that whenever the switch is closed, the output also will be one. When the switch is open, the output will be zero. And that's why we are working with base 2, because again, the numbers that we are getting is between 0 and 1. And the number that is the bit that is on the left side will be the most significant, and the bit that is on the right side will be the least significant. For example, if I have this 8 bits, 1, 1, 1, 0, 1, 0, 1, 1, this is the least significant. Sorry, this is the most significant, and this is the least significant. And now, if I want to create 26 in decimal, that's pretty easy because I just let's say I have this binary notations 1, 1, 0, 1, 0. So the first bit needs to be multiplied by 2 to the power of 0. The second bit needs to be multiplied by 2 to the power of 1. The third bit needs to be multiplied by 2 power of 2. Third bit 2 power of 3. Fourth bit to the power of 4. And that is easy to understand now. And the result will be 26. So the way that we encode information in classical computer is either by ASCII or by Unicode. If we are doing ASCII, we'll have 7 bits. So we can show any letters that we use in English by ASCII encoding. And in Unicode, we can have up to 32 bits. So basically, we can encode any language in the world with this Unicode encoding. We have some gates that are used in classical computers that are very important. Some of them are single bit, some of them are double or maybe more than 2 inputs. For example, we have an identity gates, which means that whatever you provide as input, the output will be the same. So basically, it doesn't do anything for us. We have NOT gate or inverter, that whatever you provide as input, it will just reverse that for you or invert that for you. 0 becomes 1 and 1 becomes 0. And we can have constant gate, for example, always 0. Regardless of what is your input, the output will be 0. Or regardless of what is your input, the output will be 1. And now we can have also 2-bit logic gates that are very important. And your computer is built by millions or billions of this type of gates on the CPU that is using. We can have, for example, AND gates that it takes to input and provides you like we show it like this, the AND gate. So we have 2 inputs and we have 1 output. If both of these inputs are 1, the output will be 1. Otherwise, the output always will be 0. Also, we have OR gate that we show it generally like this. And if only one of the input, if at least one of the inputs are 1, the output will be 1. And we have XOR gate that output 1 only when the inputs are different. For example, if one input is 1 and the other is 0, the output will be 1. But if both inputs are 0 or both inputs are 1, the output also will be 0. And the way that we show it is like this. This is an XOR gate. So yeah, in the again, I talk a little bit about the history of the computers. Back in 1940s, we have the vacuum tubes that used approximately 1,600 to 2,400 vacuums per machine. They were extremely large. We're talking about the size of an entire room, or even bigger than that. And they were power hungry, of course. This was then we moved on to the modern transistors, and later on, especially back in 50s and later on 60s, that we have the integrated circuits. Then we could have tens of billions of transistors just on one CPU compared to 2000 tubes in 1940s. And it takes much a smaller space. Like your laptop is very small compared to the vacuum tubes that they used in the 40s, and doing much more work. You know that your computer, your smartphone today is doing much more processing than the chip that was used for sending astronauts to the moon. So you see how significantly the size has decreased. One concept that is very important for us is universality, which means that a set of gate is universal if we can construct any possible operation with just those gates, which means that not and or are universal, which means that you can create any gate by just combining these three or a combination of these three. Or NAND gate itself is also universal, which means that you can create any gate by just combining NAND gates, which is very nice. So I can create the entire types of gates only with a bunch of NAND gates. NOR is also actually universal, and like NAND, NOR is universal. By using NOR to create NOR and OR, we prove can simulate the NOR and OR universal set. If you're wondering what is a NAND gate, it just basically is not an AND gate, which means that it just takes the result of an AND and just invert that. So if you have an AND gate and put a NOT on the end, this becomes a NAND gate. So if this input is 0, 1, the output will be 1. If the input is 1, 0, the output will be 1. If the input is 0, 0, the output again will be 1. If the input is 1, 1, the output will be 0. This is a NAND gate here. And so in machines, for programming, you can use Verilog. I mean, if you want to write in very low level programming, just like decimals, for example, we add bits right to left and carry remainders. For example, 1 plus 1 becomes 2. So in binary, we show that by 1, 0. And then 1 plus 1 plus 1 becomes 3. So that would be just 1, 1. And that will show us 3 in decimals. And we can create, for example, full adders. We can create half adders. And we can do any sorts of calculation by just combining these gates together. And the other thing that is important in your classical computer is Boolean algebra. For example, the order of operation that AND is performed before OR, just like multiplication that is happening before addition. Like, for example, if you have A plus B multiplied by C, first you multiply B and C, and then you add A to that multiplication. We have also another feature that is called commutativity, that says AB is equals to BA, and A plus B is equals to B plus A. We have associativity, that means ABC is equals to AB multiplied by C, and A plus B plus C is equal to A plus B plus C. And we have distributive loss, that means if you add A multiplied by B plus C, you can distribute A over this parenthesis. So you multiply A by B, and then plus, and then you multiply A and C here. Or you can do the same operation with OR because this is an OR operation, the plus sign. So you can basically first do an OR of A and B, then multiply that with an OR operation over A and C. And there are a bunch of other stuff like, for example, inverse is shown by A hat, like this is the inverse of A. Also, we have Morgan's law, for example, that you have AB hat over it. It can be like this will be equivalent to A naught plus B naught. Or if you have A plus B naught, it is equals to A naught multiplied by B naught. Don't worry about it if you don't know much about that. But just saying like this is the way that your computers basically, we are using Boolean algebra for reasoning and simplifying the logic. And this helps us also to simplify the circuits. If you have a large circuit, then we can simplify that calculation. So also we have a Toffoli gate. This is basically a reversible AND gate with 3 inputs and 3 outputs. It flips the third bit only if the first 2 bits are 1. Don't worry about that right now. Mainly, I'm going to talk about it later in quantum computers gates. But this is a very important gate. Later on, I'll show you in quantum computers. And also we have the class of algorithms that I'll record another video, but this is very important for us to know, especially when we talk about when quantum computers are stronger or actually can do stuff that a classical computer cannot do. So let's look at the categories here. For example, we have P class. P class are the problems that can be solved efficiently. For example, if you want to add 2 numbers or if you want to sort a database, this is not the big problem. You can do it with the classical computers. And P problems are problems where you can verify the solutions very fast, but it's hard to do the opposite, which means that you can, if I ask you to find the solution, it would be very hard. But if I tell you to verify it, it is easy. One of them is factoring. What I mean here, let's say if I give you 21 and I tell you what are the factors of that, it takes you a little bit of time to figure out that the factors of 21 are 7 and 3. But if I give you 7 and 3 and tell you what is the result of multiplication, you can quickly tell me that that's 21. Now, of course, imagine that I have, instead of a small number, I have a very huge number that has 200 digits. Let's say a number like 7, 9, 2, 3, 5, 2, 9, 6, 5, like this. And I tell you what are the factors of that. This is something very difficult. Of course, the longer is the sequence, the more difficult it is to find the factors. But if I give you the factors and tell you, are these factors really the factor for this number? It is very easy to do that. You just multiply them, and if you get the same result, then you know that it is true. Again, to put it in a simpler way, if I give you C and tell you what are the factors of that, you have to find A and B, which might be difficult, especially if C is very long sequence. But if I tell you what is A and what is B and tell you, is the multiplication of A and B give you C? That's a very easy problem. They also have BQP problems that are problems that can be efficiently solved by a quantum computer. One of them is the Shor's algorithm, because we know that Shor's algorithm can find the factors for large numbers, although a classical computer will suffer. So that's one problem that quantum computers provide the better solution. And they proves the supremacy of quantum computers for a specific type of problem. So again, I want to put it this way, that we cannot say like quantum computers are great for solving all the problem and they are better than classical computer. Actually, not necessarily they are better in solving all types of problem, but there are some problems that quantum computers can solve much more efficiently than a classical computer. Hopefully, I'll have time later on that make another video and talk more about this. It's a very nice topic, especially when you think about what type of problems are really can be solved in an efficient way with the quantum computer, and which type of problem we shouldn't bother ourselves because our classical computer is doing already a good job. Thanks so much for watching. In the next video, I'll move on more in depth to quantum computers. Have a great day.